Hello. In this video, we're going to briefly study a pattern, a very ancient pattern, known as Pascal's triangle. So the way it starts is you have the number 1, and then in the next row, you put another couple of 1s, and in the next row, you put another couple 1s, but this time you have room for 3 numbers. You have a 1 on the outside, a 1 on the other outside, and you have room for a number in the middle. Now, if you put another 1 here, you would just have a big tree of 1s, and that would be a bit boring. So instead, what we do is we take the number here and the number here, and we add them together to get the number right here. So our next row is 1, 2, 1. All right, let's continue the pattern. We'll put 1s on the outside, but now to get the numbers in the next section, these two have to get added together. And these two have to get added together. So that's going to give us 3 and 3. All right, the next line would be 1, 4, 6, 4, 1, and so on. Go ahead and continue the pattern yourself for a few more rows and see what you come up with. All right, so you should have something like this. Here is Pascal's triangle all the way down to 1, 14, 91, 365, 4, 1, 0, 0, 1, and so on. A giant triangle full of interesting numbers and number patterns. Now, what do I mean by interesting number patterns? Well, if you notice right away, down the side we have all 1s. Maybe not the most interesting pattern, but hey, it's something. Down the next diagonal, we have the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Those are pretty interesting. Now, what other patterns, though, might we find in this triangle? Let's start with powers of 11. So let's take 11 to the power of 0. That's going to be 1. 11 to the power of 1 is 11. 11 to the power of 2 is 121. Oh, 121. I wonder what 11 to the power of 3 would be. Let's type it in on our calculator. That means 11 times 11 times 11. That's going to be 1331. How interesting. How interesting. What about 11 to the power of 4? You betcha it's going to be 14641. Now, unfortunately, the pattern breaks down with 11 to the power of 5. Because after 5, you're going to have a bit of a carry, and so it doesn't quite work with the next one. But if you do 11 to the power of 5, you get 161051. What sort of happened is this 10 is kind of rounded up in the 5 to make it a 6. But yeah, we have, at least for the first few powers of 11, they all show up in this table, and you can kind of make that last one work if you fudge it a bit. That's kind of neat. Let's look for some other patterns. Let's clear this off for a second. What if we were to take the rows and add them up? So this row adds to 1. This row adds to 2. This row adds to 4. Oh, interesting. This row adds to 8. What do you think the next row adds to? Well, this is going to be 5 and another 5 and a 6. That's 10 and 6, 16. Oh, weird. If we add up all these numbers, I think we're going to get 32. And indeed, this pattern will continue all the way down. Every single row adds up to a power of 2. Well, that's pretty cool. What other patterns can we find in here? Well, again, let's go ahead and clean these off. Start with a fresh triangle, and let's draw a little hockey stick. So imagine we're going to start here with our hockey stick, and we go down, 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 down. Boom. We can see that we have sort of this hockey stick pattern, right? Just like that. Looks like a little hockey stick. And in our hockey stick, we take the numbers along the handle and add it to each other. So 1 plus 3 plus 6 plus 10. That's going to equal 20. Surprise, surprise. That's the number at the tip of the hockey stick. Let's try a different approach here. where do we want to start our hockey stick? Maybe we'll start it over here. So we go 1, 6, 21, 56, 126, stop. Let's draw a little hockey stick there. Well, 1 plus 6 plus 21 plus 56 plus 126. Yep, that checks out. That's 210. This is sometimes called the hockey stick pattern. You can draw any kind of hockey stick you want as long as you start from one of the outsides. As long as you're starting right at the edge with the 1. You can draw as short as you want. There's 1 plus 5 equals 6. Or as long as you want. And you're going to get the numbers in the handle equal to the number at the tip of the hockey stick, or sometimes called in the blade of the hockey stick. All right, let's see if we can find some other patterns here. Let's try typing in on our calculator 7C3. 7C3. It's going to give us 35. Well, if you notice, there's a 35 in the table. That's kind of strange. Let's keep the 7 constant. Let's try a few other numbers. Let's try 7C0, 7C1, 7C2. Let's try those on our calculator. 7C0 is 1. 7C1 is 7. 7C2 is 21. Whoa, those are the numbers across a row. Now, the 7 here is a little weird because if you count the number of rows, 1, 2, 3, 4, 5, 6, 7, 8. We're actually in the 8th row. And if you think about it, the 3, well, the third entry was the 21. So for both of these counting, we kind of have to think of starting at 0. So it's sort of like this is the 0, the 1, the 2, the 3. So it's like not really it's sort of like the 4th entry, but it's like the 3rd entry if you consider the 1st entry to be 0. So it's like 7C0, 7C1, 7C2, 7C3. And we could try 7C4, 7C5, 7C6, and 7C7. We can try those on our calculator. 7C4, yeah, it's 35. 7C5, yep, that's going to be 21. 7C6, that's 7. And 7C7, yep, that's 1. So the whole row here, the whole row is going to just be your C's. And again, while it's technically row 8, you can think about it as if this beginning row was like the 0 row. But it's the row that has a 7 in it, or it's the row that has 8 entries. Again, this will be the one that has 7C something. And this works with any row. So down here, if you look, this is the row that has an 11 in it. So this should be the 11C something row. And maybe we wanted to find the 330. So this would be 0, 1, 2, 3, 4. So I think 11C4 is equal to 330. Let's check that on the calculator. 11C4. Yep, 330 for sure. And it's interesting that there's another 330 over here. This would be 11C0, 1, 2, 3, 4, 5, 6, 7. 11C7 should also be 330. 11C7, yep, that's 330 as well. So if you notice, 11C4 equals 11C7. They're kind of like mirror images of each other on the triangle. If you were to imagine a giant mirror down the middle here, everything on either side is a mirror image. We can see it visually, and we can also see how it works out with the math. So this is pretty cool, Pascal's triangle. It gives you some interesting number patterns. It allows you to connect to some permutations and combinations. There's not really any notes that you would use per se on something like this, but I wanted to introduce it to you because you're going to see in the next lesson that not only is Pascal's triangle interesting, not only does it have some really cool number patterns, but it also is going to allow us some shortcuts when it comes to expanding binomials. So stay tuned for that on the next lesson. If you did want to do a little bit of practice, you could look at worksheet 10.5, which has some practice with expansion. And you could also write out the triangle again, just for good practice, so you have it handy. All right, hopefully you enjoyed that video. And as always, thanks for watching.